All right, let's talk about implementing Gemini Robotics, the phenomenal paper from Google DeepMind, and yeah, how to reproduce it, how to implement it. Like one of the nice things about Gemini Robotics is the embodied reasoning. So they talk about how Gemini directly from the like a vanilla Gemini Flash model or even Gemini Pro model can do like 2D object detection. It can point at the shirt and tell you which are the best points to start folding the shirt. It can do 3D object detection, multi-view analysis. And then they use their robotic data set, which is like a year of data, like 10,000 hours of data set, to fine tune it to be even better at embodied reasoning, right? So we're going to directly go into the Gemini robotics, the main part of it, which is the foundational models for robotics. And maybe in the end, we can come back to everything else in the paper, right? So when they talk about Gemini robotics, the foundational models, this is how the architecture look like for it. They have a cloud backbone, which is basically a Gemini model, which is fine-tuned on the embodied robotics data set. They call it Gemini ER, embodied reasoning. Then they have a local action decoder, which is a Gemini model distilled. And when I say Gemini model, I think it's Gemini ER model. So it comes with all the goodies of embodied reasoning. And distilled in terms of it's pretty small, it should run locally, where Google claims to get like 250 milliseconds of latency. Yeah, 250 milliseconds of latency together with the local model and with the backend model. Now, I couldn't find anywhere which hardware they're using to run it, but I'm assuming like the consumer GPU should give you that kind of accuracy. Now, one of the interesting things, or like one main difference between foundational Gemini model and the CRUD or pi0 is that here you have a cloud backbone, right? You have a massive VLM which sits on the cloud, as opposed to pi0, yeah, where you just have a local VLM together with the action expert. Same goes for the CRUD. They call something like System 2, which is VLM, and System 1, which is the action decoder, like a diffusion transformer. But with Gemini, you have like another model which sits on the cloud, like another VLM, like a massive VLM. So you have two VLMs. One is VLM in the cloud, another is the VLM which is distilled from the cloud VLM to run locally. Now, the nice part of it is like it comes with like a lot of horsepower. Now, how it works is that the cloud VLM takes the images and the and take the images and the task and then breaks it down for the local model to implement. Now, when you talk about like breaking down the task, it is not just giving the subtask. Trying to look for the model car. Yeah. It's not just the subtasks that the models break down, that the models break down. So Gemini ER, Gemini Robotics Embodied Reasoning. Yeah, it takes the model text, yeah, and images. Yeah. Yeah, since and so Gemini ER outputs the text, which is basically most likely the subtask, and along that the numerical coordinates. So when you talk about the numerical coordinates, that get pretty interesting. A lot of people assume that there's no like the way we did classical conditioning in the robot is giving bounding boxes, basically helping the robots to make decision, is segmenting depth that we don't do it anymore. And it kind of says that like a lot of like this is how you would do it when you implement something, deploy something, especially to make it like more generalized or redundant. Like you point to things, you figure out like you output ideal crossing coordinates, you output ideal trajectories, you output ideal future scenarios for bounding two boxes or 3D boxes. So this is what the Gemini Robotics AR, the cloud backbone does. And then I don't know why Google names it like that. So you have Gemini, and then the local decoder, which is called Gemini Robotics, takes that along with the robotic observations, basically the images and the state input, and outputs the action, right? So we're we're gonna try to implement something similar. Now, I don't have access to the fine-tuned ER model, neither do I have access to Gemini Robotics model, but I do have access to Gemini Flash via the API and Gemini Robotics, which is like the local decoder. Uh, It's more or less something similar to the pi0. So what we're going to do is we're going to take pi0 as our Gemini local decoder, and we're going to use Gemini Flash as it is without any fine-tuning because you can't, as the ER, as the cloud backbone. Now, yeah, the whole code is based on the lerobot framework from Hugging Face. So I'm hope you're like acquainted with the system. You have S100 or S101 ready. You have done some kind of ACT fine-tuning, so we can basically go into it. Yeah, this is what I was talking about, like spatial understanding of the Gemini model. And we can go back to it. Now, I can just quickly go over it. So Gemini model, just out of the box, is pretty cool at the spatial understanding. It gives you, for any general scene, it can point at the objects. You don't have to tell it. Like you can reason it. Like it can tell me, you can say like point at the objects which will help me make coffee, or like point at the objects that I can use to make coffee. It will tell you, it will show you like coffee maker, maybe one stove, because technically you can do. They have two stoves here. Funny. It does pretty good 3D bounding boxes. It also does like reasoning around yeah, here, like the main body of the clamp, shape like C. It also gives you like trajectory, it gives you grasping points, and that's what I'm using to collect the data set, basically to get the conditional data set, bounding box conditioning. For now, I'm just doing 2D bounding boxes. I think that's enough. It's inference. So when I show you the script, like how can you implement something like that? So if you are building, like the first part is obviously data collection. So we have a Gemini script here, which gives you 2D boxes for all the objects in the scene. Yeah, then I'm also drawing the boxes. That's basically for visualization. And I have something called getting random boxes, because when I'm doing pick and place, I don't want to see all the bounding boxes. I just want to see one box, which I know that I want to pick that box. Basically, then get the next box to know which object to pick. Basically, optimize the daily operation of data collection and have like only one bounding boxes, which then matches the daily operation. So this is how the control util files in the lerobot library should be updated. So what we are doing here is, like, one of the things I'm updating is yeah, here. Just in case, if you're using pi0 or pi0 fast or any of the foundational models, you need to update, like, add this small line for your in your controls policy, because the foundational models need a task, need a subtask. But yeah, so you could automate it for now, just to make it easy for me. I have a space bar. Whenever I collect a box, I collect the object and drop it into the place location with robotics. I use a space bar to initiate the next object. Another modification in the control utils is like having a small sleep time in the warm up, because sometimes before, like, it takes like a moment for camera to initiate, and the framework was already passing my image to to Gemini, which was giving the error. So I added a small time slip. But main part of the code is here. Main part of the course. See, the main part of the code is here, like main meat of the code. So assuming we're doing box augmentation, so getting some kind of conditioning with Gemini, this gives you the target bounding boxes. So you get pick object and place objects. They both are also normalized, and you also have the labels. Now you pass them on to get random target, to collect any one random pick target, like single target, and a single place target. Once again, this is for teleoperation, for collecting the data set. Now, based on our pick target and place target, we also modify the 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 task input, like what is the task called, the annotation of the task. And that's quite important for training the foundational models, because they're conditioned on the task too. Yeah. Um, Now another important part is when you collect the robot state. So we're collecting this. We have the robotic state, and then we are augmenting the robotic state with the pick bounding boxes and place bounding boxes again, which are normalized, just easy to work with machine learning algorithms if you normalize values. So when I say pick and place, it basically I'm pick like a pick object, basically object I'm picking, and place object is the location where a place is basically the location where I'm dropping that object. Now, this code example is only for pick and place, but like go ahead and modify it for however you feel like. Yeah. Now, another modification is here in the visualization part, where I'm plotting every time a single bounding box for the object that we're picking and the location where we're dropping. So when we're teleoperating, we know which object to pick and where to drop it. And in the end, we have events here where every time I pick an object and drop it back, I just use a space bar to iterate and go to the next object. You could automate it probably, but yeah. So once you collect the data, you can fine-tune your pi0 policy, and you can directly do it by lerobot, like the classical script for fine-tuning is like absolutely fine. It works really nice. Just remember that here you should change from policy type to the policy path. So you don't train the pi0 policies from scratch, which doesn't work so well. Like a big giant model. Give it like the pi0 path, which is I think lerobot/pi0, and you can then fine-tune the pi0 policy. Now, once you have a fine-tuned pi0 policy, you can then do the inference in a Gemini, the way that Gemini Robotics people are doing it. Where did I yeah, here. So yeah, obviously, like you can run the inference script, the eval script, which is perfectly fine. If you're doing that, if you're running the eval script, remember to um, modify the control utils file at this location, at the capture observation side here. Because now this file is only modified for the sake of teleoperation, for collecting the data set, and not for running the evaluation, for running the policies for inference. Like I normally prefer to do a lot of things in Notebook. I don't know it's a good idea or bad idea, but I just prefer notebooks. So yeah, here we go. With seeing up listeners, one of the things I forgot to mention is I'm using only single camera for now, but we'll update the code to do multiple cameras very soon. Uh, Pass on your policy, load your policy. This part is if you want to go into this agentic side where you don't have to give the task, but just talk to the robot like, hey, do this for me, do that for me, or give me all the material that I need for making a coffee, and it will basically pick out all the stuff that you need for doing a coffee. You can then suggest a prompt, and here you start it. So you capture like your first observation. You pass it on to Gemini, which gives you all the bounding boxes, and then you basically iterate over, which gives you all the boxes for that task. It gives you all the objects for that task. Considering if you're building a red Lego toy and you're asking for bricks for those toys, it will understand which bricks to pick up and which bricks not to. So it will give you exactly those bricks. And then if you want them to be dropped in blue container or red container, you can just tell it and it will then give you like that bounding boxes for that container. Now, based on that, then you can iterate the inference to pick like one brick, another brick, and drop it into the box that you want to. Once again, we are modifying the task here, and modifying the observation state to take in the pick and place of where to do that. I need to go back and do add the place normalized bounding boxes to it. Have the same event trigger management here. Like every time it drops a brick, I just use a spacebar, but you can try to automate it. I didn't do it because I'm just saving on the API calls. So the thing is, because of the rate limit that Google has, it's kind of, I mean, everything you do with the Gemini for this kind of experiment is free because they have like, I think, 1,500 calls per day, which are free. Obviously, as soon as you start using it heavily, you have to pay for it, but I think the cost is fine. So instead of just doing it once, which has a lot of drawbacks, like if if in the action the objects move around a lot, the robot doesn't generalize well. So it makes sense to have Gemini more in the loop, which you can do once again, depending upon like what's your budget and how are you just experimenting or you wanna like are you building something pretty neat for deployment? That works a lot. For me, I'm just experimenting and just wanted to implement something like what they were doing. And I found that it generalizes like really, really well, which was really surprising to me. So that is part of the Gemini we talked about. And other things that they do in the, did I miss something? Yeah. And yeah, like if the nice part is when you're conditioning with you don't have to just do bounding boxes, but try different things, trajectories, the grasping points. I found like grasping points is a pretty neat thing to do. Grasping angle wasn't working for me, at least not with the Gemini 2.0 Flash. Maybe it works with Gemini 2.5, or maybe you need the embodied reasoning fine-tuned model for that one. Now, the other interesting parts, so one of the main parts is basically the reasoning. Another interesting part is they talk about chain of thought reasoning. So even like in this case, the chain of thought reasoning works like much better than the vanilla prompting. And then they ran two different experiments, which was where you give Gemini directly the API to control the robot, which works like 50% of the time dimension and 60% of the time for the ER model. Another was by giving some example prompts. But I really like the whole Gemini robotics interface, and I also find it pretty interesting that thanks to the open source community, thanks to lerobot, thanks to pi0 people for open sourcing pi0, once again for the Gemini team to have the rate limit so you can try some things for free and experiment a lot. And you can build a current state of art model from your desk, and make and build cool things. Am I forgetting something? Yeah, this it's just about the documentation, about using like multi-view Gemini policy. So Gemini has this really cool multi-view where you can show it like image one, take output from it, then go and show it image two and take output from it. And like I had a very cool use case for it. For example, if you look at the data augmentation, so you have this diffusion rosy paper, which is quite old, like it's like 1.5 years old, but in terms of AI, it's like quite old. Yeah. But yeah. And when I looked at all these in-painting papers for data augmentation, I found like everyone uses only single camera when it comes to image augmentation or data generation using in-painting. And that makes sense because if you have multiple cameras, you have this consistency problem between the camera views. And I was able to solve that using the multi-view from the Gemini side. I don't know where I can find it. Yeah. And what I did was so I took the image from the front camera and had a Gemini multi-view look at the front camera image and I look at like which is the good part to locate the object. Then did the inpainting and took those coordinates and basically wrap those like because now it can exactly understand in like the top image that's different view using this multi-view from Gemini. It can easily spot like what points from both image like these are the same points in two different images. So it can do this future mapping for you. It can tell me exactly where those objects where should I inpaint the distractions or what are the things that can I inpaint, and that worked like a charm too. So there are a lot of interesting things you can do. On one side, it's like a hammer where every problem is a nail to you. You can just throw a VLM at it. It's probably a nice idea to build a smarter solution. But at other side, you can actually build a lot of cool things a lot more easily now, thanks to all this open source and smart AI VLM models. Um, yeah, that's it for now. And I'm gonna try to publish everything here in the Robot Builder notebook. This is just like a small course I'm doing at the HPE here, like Hasso-Plattner Institute in Berlin, around AI and robotics. And as we progress to the course, I will make sure that I keep the repo updated with the videos, with the lessons, with the scripts and everything. All right. Thank you.